In this lesson, we're going to look at quantum numbers. Essentially, what quantum numbers do is they provide a description of an electron within an atom. So we'll write that over here. Provide a description of an electron within an atom. So there are four quantum numbers that we're looking at, and the first quantum number is the principal quantum number. So this should look familiar to you because this is also what existed in the Bohr model of the atom. So this was preserved from the Bohr model to the quantum mechanical model of the atom. So this is the main energy level of an electron. It's represented by the variable n. Okay. It's also called a shell or energy level, and it also describes the distance from the nucleus, right? So 1 being the closest to the nucleus, 2 being further away, so on and so forth. So distance from the nucleus is given by the principal quantum number. So we have these numbers, n is equal to 1, 2, 3, and 4. Principal quantum number is also sometimes given these letters, K, L, M, and N, K being the first energy level, L being the second energy level, third, and fourth, these capital levels here. You'll also see this in the readings that we've provided. So the secondary quantum number shows that within an energy level, so within the first energy level and the second energy level and so on and so forth, there are actually subshells. So there are sub-energy levels within each energy level. The secondary quantum number is given by the variable L, and for each value of n, there are the same number of subshells. So what I mean by that is in the first energy level, n is 1, there's 1 subshell. In the second energy level, n is 2, so there are 2 subshells, so on and so forth. The numbers of L can go from 0 all the way up to n minus 1. So the relationship between n and L is equal to 0, 1, 2, 3, all the way up to n minus 1. So I have this table over here, and we can actually show this relationship using a table of values. So if I look at the first energy level, the first shell, n is 1, so there should be 1 subshell. And if I look at this first number here, I'm going to assign it 0, right? That's the relationship between n and L. L is equal to all the numbers up to n minus 1. So if n is 1, L can only be 0, right? 1 minus 1 gives me 0. In the second energy level, again, I should have 2 subshells because it's the same number of subshells. So I have 2 subshells, so I'm going to go from 0 all the way to n minus 1. Well, if n is 2, the highest I can go is 2 minus 1, that's 1, so I'm going to have 0 and 1. Then in the third energy level, I can have 3 subshells, and you may have guessed it already, 0, 1, and 2. Now, they're given numbers because they're quantum numbers, but they're also given letter designations as well to show like the family of shapes that these subshells belong to. So 0 is the S family of atomic orbitals. So the first energy level only has S subshell. So it only has a spherical subshell. In the second energy level, it has an S subshell, but it also has a P subshell. In the third energy level, it has an S subshell, a P subshell, and also a D subshell as well. Okay, so we're looking at energy levels and subshells, and if you're wondering what S and P mean, well, we've seen S and P before. They are these right here. So the first energy level only has this spherical subshell because it only had the S subshell. Look at your note. The second energy level had S and p, 0 and 1. So it has, the second energy level has an s subshell, but it also has p subshells as well. The third energy level has an s subshell, it's got a p subshell, and it has a d subshell as well. So all these orbitals. Now you might be wondering, like, why are there so many of them? And that might lead, or that will lead rather, to our next point, which is the magnetic quantum number. The magnetic quantum number is basically an indication of the number of orientations in 3D space. So this is another quantum number that we're going to take a look at here. It's represented by the variable m sub l, and it can range from negative L to positive L. And so again, ml gives us the number of possible orientations in 3D space. Okay, so we look at L, and L is 0. 0 represents the S subshell. So let's figure out, using this relationship here, if L is 0, m sub L can range from negative L to positive L. So from negative 0 to positive 0. Well, negative 0 to positive 0 is just 0. So there is only one orientation in 3D space. Okay, so the S subshell only has one orientation in 3D space. That should make sense, because if we go to look at it, the S subshell is just a sphere, and there's only one way we can orient a sphere in 3D space, and that's centered around the origin or centered around the nucleus. So the S shell has only one possible orientation in 3D space. One represents, as we can see up here, one represents the P subshell. So that's the P subshell. I look at this relationship, and I can go from negative 1 to positive 1. So I go negative 1, 0, and positive 1. Okay, I have three numbers here, so that means the P subshell, or the P orbitals, can have three possible orientations in 3D space. Let's go and see what they are. I go back to my P. Oh, look, there are three orientations in 3D space. One where the antinodes are along the x-axis, one orientation where the antinodes are along the z-axis, and one orientation where the antinodes are along the y-axis. Okay, so we can actually even write that in. Okay, one for along x-axis, along the z-axis, and along the y-axis. Three orientations in 3D space. All right. 2 is the letter designation for the D subshell. We look at the relationship. It can go from negative L to positive L. So we have negative 2, negative 1, 0, 1, and positive 2. So it looks like there are 5 possible orientations of the D subshell in 3D space. Let's take a look. I look at my D subshell. Yep, indeed there are 5 different ways the D subshell exists. And each of these exist. So there's one where the antinodes are along the XY plane, one where the antinodes are along the XZ plane. There is this one right here, the DZ squared, where we have antinodes oriented along the Z-axis. YZ, where we have antinodes along the YZ plane. And then this one right here, where the antinodes are directly on the X and Y axis. So 5 possible orientations of the D orbital, the D subshell. So 3 is F. And as you may have guessed, there's going to be negative 3, negative 2, negative 1, 0, 1, 2, 3, 7 possible orientations in 3D space. The last quantum number that we're going to take a look at is the spin quantum number. And we know that electrons can spin what we call counterclockwise and clockwise. So it like essentially spins on an axis. And so the fourth quantum number is represented by the variable ms for magnetic spin. Since it only has two possible spins, its values that are given are +1/2 and -1/2. Okay? Alternatively, this is given in diagrams as an upspin or a downspin. Okay, so clockwise or counterclockwise. So in conclusion, an electron within an atom will have a distinct set of quantum numbers to describe its specific energy. Okay, and we can write over here, no two electrons have the same set of quantum numbers. Okay, looking at the next page right here, we have a comparison of orbits and orbitals. So orbits are what we spoke about in the Bohr model of the atom, and they were basically 2D paths or 3D shells around the nucleus, whereas orbitals we now see are basically 3D shapes of electron probability. The orbits had a very fixed path and fixed distance around the nucleus. We can picture that in our head of these electrons moving in a circle around the nucleus, whereas orbitals are essentially enclosed spaces of high probability. So instead of these like fixed pathways, they are these like nebulous regions where we are likely to find an electron. Orbits were typically circular, but orbitals have different shapes depending on the quantum numbers. Recall, these shapes are generated by Schrödinger's wave equation, and we can see that right here. Look, these orbitals all have a diversity of shapes. Now, some of them have similar shapes, but they're just oriented in different positions along, say, the x-axis, z-axis, y-axis, or along the xy plane, xz plane. But they are, you can see that they differ from each other. Okay, going back over here. In orbit, we say that a 2n² number of electrons per energy level or per orbit, right? So in the first energy level, right, when n is equal to 1, we can only contain 2 electrons. In the second energy level, we can contain 8 electrons. And in the third energy level, we can contain 18 electrons. In orbital, each of these shapes here, we've said this already, each of these orbitals, each of these shapes only contains 2 electrons. Okay, so we're going to scroll back down to that table. So an orbital can only have 2 electrons per orbital. So the quantum numbers now have specific meanings in terms of electron clouds and shape. The principal quantum number is n. It's the main energy level of the electron. It gives the distance from the nucleus. And we have, for example, values 1, 2, 3, 4, so on and so forth, also given by the letters K, L, M, and N. The secondary quantum number is given by the letter L. It's the subshell, and it essentially is the family of shapes orbitals. Okay, so when L is equal to 0, that's my S family of orbitals. They look like spheres. Some of them have a radial node, some of them don't. We'll show the relationship later. When L is 1, that is my P family of orbitals, one oriented along the x-axis, one oriented along the z, so on and so forth. And then 2, that's my D family of orbitals, right? And we saw that there were 5 possible orientations for all those D orbitals. Magnetic quantum number, it gives you the orientation in 3D space. Recall that m sub L can go from negative L to positive L, and it gives you all the different possibilities of orientations in 3D space and how many individual orbits there are going to be, or rather orbitals there are going to be, right? So if we look, right, if m sub L is equal to 0, there's only going to be one orbital because there's only one possible orientation in 3D space. When m sub L, you have -1, 0, and +1, right? And that's for the P subshell. There are going to be 3 orbitals, right? That's for the P subshell. Electron spin is pretty easy. It's just +1/2 given as your clockwise or up spin, -1/2 given as your down spin or counterclockwise spin. So these are your sets of quantum numbers. The subshells can be represented by the secondary quantum number and can be further described by the following letters, right? So 0, we've said this already, is given by S, right? It's the S family. And how many orbitals are in the S? Well, just 1, because there's only one possible orientation in 3D space. 1 is P. Remember that the P orbital, or the P subshell, can have 3 possible orientations in 3D space. So we have 3 orbitals. D can have 5 orientations in 3D space, and so therefore 5 orbitals. F can have 7 orientations in 3D space, and therefore 7 orbitals. And within this subshell, S has the lowest energy, followed by P, followed by D, followed by F, and so on and so forth. So this right here, S has the lowest energy of these subshells, whereas F has the higher energy of the subshells. So this concludes looking at quantum numbers.